climate risk management. Imagine this is the distribution of seasonal rainfall. So it's not always wet, right? So there will be times that will be wet, there will be times that will be dry, too wet and too dry. So meaning across this spectrum of rainfall distribution, you will have times that you will have hardship or crisis. Even at the right-hand side of the distribution, these are also extremes that can produce events that can damage your agricultural production. So, farmers, decision makers, they have different decisions to be done. So it depends on what the decision scale you're looking for, if it is the local scale or regional scale. Usually farmers, they are more interested in the strategic and tactical decisions being done in the farm. For policymakers, i.e. food security and contingency planning, targeting, resource mobilization. So planning and either to stock or export, something like that. So why we use models or crop models in this case? Because if we can quantify the impacts of these climate events, then we have more objective decision-making process. This is a simpler cartoon of how to manage the full range of variability. This is a time series of seasonal precipitation in an arid area in India. You can see that in the 30 years of data, you can see a lot of fluctuation of the seasonal rainfall. Sometimes, most of the decisions they say are based on average, but if you look at this, where is average? It's not here, right? Because if you base your decisions on average, when the situation is favorable, you will forfeit the benefits. And when the situation is bad, then you will expose your system into risk. So and this will enter, the utility of seasonal climate forecast, because it's the variation that you have to use or predict. And if you have the ability to predict the variation, you will have the hand of trying to reducing the risk due to the variations in climate. However, even if in the same season you have the same amount of rainfall, the daily variability is still different. So that will also entails a different approach in managing the risk at the subseasonal time scale. So average is not representative. There is information in climatology. So this was my question before to Allard. If in areas, because skill is very important, but it depends on region and season. So in areas where there is low skill, what can we do? Information from climatology may be useful. And I will, in the course of my talk, I will try to show some examples on how we use monitored information to improve the information coming from climate. And if, for example, there is skill in forecast, information from climate forecast will be useful. So I will go through my slides, informing decisions at the local scale. So if you are a farmer, what are the decisions that you are going to make in the growing season? Strategic, these are the long-term meaning seasonal or 6 months or a year. Seed investment, fertilizer, insurance. Tactical, when, to, right? Plant, irrigate, fertilize, harvest, and how much to irrigate and fertilize. So some, couple of case studies and how you can use, if you want, climate information in fertilizer management. So these are actually experiments in dry land agriculture. Is different probably from your situation here in Korea. And then I will present what I call a risk index for planning optimal sowing window, and then show how can we use this risk index for planning supplemental irrigation, optional supplemental irrigation in dry land agriculture. This is an example of using a crop simulation model, in this case a model for maize, and how you can use climate information to inform your fertilizer management. So what I did here is I have 30 years of data, weather. I run the crop simulation model for different density, plant density and different fertilizer management scenario for a particular variety of maize in Malawi. I ran it 30 times and tried to come up with this plot. Actually, this plot shows the risk-efficient management strategy when, for example, I use information only from climatology, or if I divide my climate data into an El Nino or ENSO phases, like El Nino, neutral, or La Nina. What you can see here is, this is actually the x-axis is the fertilizer rate. This is your gross margin in terms of their local currency. And this is the yield. So this one shows the gross benefit, meaning you have your yield, and then you deduct the yield plus times price and deduct the cost. And this one, I think this is the total cost, and this is the yield. So you can see here that the best decision in climatology, using climatology, is not actually the best decision during a dry phase of the climate. What he's saying here that during dry phase of the climate, don't invest much in fertilizer because it's going to be risky anyway. So if you invest less, you will have more benefit in terms of money, right? And other phases of the climate will, what is interesting here is there is a variance here because this is from the 30 years of data. So you can just say, okay, in here, this is the expected benefit when you are using this management strategy. Okay, so, and now this is an example of how I use a crop simulation model to devise what they call a water stress risk index. It's like similar as your WSI, but I use the ratio between the actual ET and ET crop, right, as a basis of my stress, and then 1 minus. So basically, these plots, these are the plots. In this case, I show here only 10 years so that it will be easier to understand. So I have here daily water stress for 10 years at a particular sowing date. And then what I consider as index is I take the probability of exceeding a threshold. So this threshold may be variable to different crops. So I choose 50%. This is fair, I think. So if you see here how many times this is exceeded, because the higher the value, the higher the stress experienced by the crop, because I deducted from 1, right? So how many times? On this particular day, when I planted in this particular sowing date, there are 3 times that this threshold had been exceeded. So about 33%. So based on climatology, or in this case, 10 years of data, I expect that in this date, based on historical record, it is very risky for the plant, okay? Now, how can I use this? Okay, for strategic decisions or tactical decisions. I run the model, and then for different planting window, so you can move this as a window in your planting, and then you can basically map the stress index and then overlay it with the growth stage in the crop. And you can see that during this planting window, it is riskier here. I mean, the plant will experience high risk or high probability of exceeding a stress above 50% during this period. And then you can basically move that, and then you can have a plot of the yield here, so you can see the response of the crops. Okay? And then what I did here is I look at those stresses and try to correlate the yield response at different growth windows. And then you can see that during this period, the correlation of the yield and the stress index is very high. So one application of this, you can use it for yield prediction if you want, because there is a strong negative correlation between the stress during these periods. But you can see that different sowing dates, they have different response. But this is from the model perspective. how I use this for defining optimal irrigation, and then optimal supplementary irrigation, and then how I can show the value of seasonal climate forecast or information in this application. So what I did is, this is again an example in India. I tried to characterize the climatology of the onset of rainfall. So our Indian counterpart said that, okay, how do you define an onset of rainfall? Agronomically, what they said is, if the rain total is already 75 millimeter, then we say it's onset. But if you look at other definition of onset, there are other complex definition of onset. So I use a simple definition, which is greater than 75 millimeter, and from the 30 years of data, I tried to categorize the onset of rainfall using a simple tercile division. First tercile, second tercile, third tercile. And these actually are the dates of the onset from the 30 years of data that corresponds to these tercile categories. So I run the model using the 30 years of data, and then I defined what I call a risk profile for all years for a specific date. In this case, I used the mode of this particular category. So basically, you're saying that this is a representative profile of the showing of this set of onset dates. This is the risk profile when it is the third tercile, second tercile, and first tercile. How can you use this for irrigation application? So you can see here that there is a point in time where it peaks, right? So if this could be, a point in time where you can apply supplementary irrigation, because when you apply supplementary irrigation, you will reduce these peaks. Okay, but that is considering all years. There's no seasonal forecast here. So then I said that if it is conditioned an onset of rainfall, so only, for example, if this season I monitor the onset to be third tercile, or you can use a forecast of the onset. So assuming it is a perfect forecast, so I run the model using that I know that it is at the third tercile, and this is the specific index based on the third tercile, okay? And then, okay, I can enhance more my irrigation application to here. And then I run a simulation wherein I have what I call risk intervention analysis, and I design no irrigation at all, and the irrigation scheme based on climatology alone, meaning I use all information from all years, or from the forecast. And you can see that from no intervention to with intervention, but different sources of information from climatology or from forecast. So this is one way of showing how forecast can inform your decisions if the forecast is skillful. So that is a very big explanatory point there, if the forecast is skillful. Okay. Sorry, I have to drink some water. So I walk you through some of the studies we've done at different scale, policy scale, regional scale. So as I've said a while ago, this is where your seasonal climate, this is where your crop forecast will enter, right? Food security. So what are usually the decisions done? Contingency planning, targeting where to focus your resources. Of course, it is related to resource mobilization. Some of the studies I will present on our work in Philippines and Brazil. And then I will touch base a little bit on this one, remote sensing, agrohydrological modeling. So the work we've done in the Philippines is just very simple. There's no crop modeling involved. It's just statistical analysis, trying to see the predictability of seasonal rainfall and translate that to the predictability of rice. So in this figure, you can see the production of rice in the past 30 years for July and December and January and June. What is this? Yes. So This is yield, and this is area. So you can see that irrigated, rain-fed, the yield actually is like this. Did not improve a lot, although you can see some improvement because of the improvement in technology, probably improvement in cultivar. Irrigated yield, a lot of improvement in there. And this is all ecosystem. You can see that there is an increasing trend in the yield, and hence you can see here increasing, oh, sorry, this is production, rather. This is yield, improvement in yield. This is production. So the production in rain-fed does not improve a lot because the area actually diminished over the year because of the conversion of the land to real estate and so on and so forth. There is an improvement in the irrigated area, so the total production of irrigated area also improved over the years. So our first step is try to see the predictability of seasonal rainfall. This plot actually shows how rainfall is predictable in the Philippines. This plot shows the predictability, potential predictability of rainfall occurrence, amount, and intensity. This is based on the, so we have 77 stations of rainfall in the Philippines. Climate in the Philippines is very complex. Where here in this region you have a pronounced wet and dry season. Here you have always wet season here, and yet here you have in between. So it's very, very challenging. But what we did here is we tried to look at the standard anomaly index of rainfall for different seasons. Two methodologies that we use to try to see the predictability of rainfall is what they call the variance of the standard anomaly index and the degree of freedom. Variance is just looking at the variance of your anomaly index. Degrees of freedom is how many, if you use EOF, how many principal components is needed to explain the most variance in the rainfall. And the dashed line actually represents the degrees of freedom. The more the principal component used in your EOF analysis to explain the most variance, meaning the less the predictability is. And actually, for the variance, the less the this is bold line is standard anomaly index. So the, what is this one? Anyway, during this period where you have more members in your PC to explain the rainfall, is the rainfall here during the season is less predictable compared to this season. And that is actually shown in this relationship between rainfall, amount, intensity, and the occurrence using the seasonal temperature at the NINO 3.4 index in the Pacific. So you can see the correlation here is only 0.2, and you have a strong negative correlation outside that season. And then we tried to develop a simple statistical prediction model for rice using statistical indicators like the warm water volume and zonal wind. And these are temperature based on NINO 3.4 and some GCM for different seasons. And you can see here the correlation of rainfall actually and rice for dry season, January to June. It is interesting to note that for the rain-fed season, for example, there is a strong correlation of rice and rainfall during the dry season. Meaning, if the rainfall before the dry season is high, then you can basically have a strong correlation in yield and rainfall. So based on that conclusion, we developed a simple regression model for rice production in the Philippines. Not perfect, but you can get a correlation probably of 0.8 or 0.6. And this is for the different season. This is for the wet season, which is more challenging. But what is interesting here is, for example, in the irrigated system, this is the correlation of rainfall and rise. The rainfall, this is very interesting because the correlation of rainfall and rise goes down drastically in the typhoon season. So which means that, you know, these events probably is contributed by flood or wind. These are actually correlation of actual production in the Philippines and the rainfall. Then, you know, using some simple statistical method, we develop some, you know, these are only the result of the regression model that are significant. So we can only predict these regions in the Philippines for rice. So that is a statistical method, just purely regression model. This is probably more similar to what FuseNet is doing. So what we did here is we developed a simple regional mechanistic soil-water balance model, and then using the fluxes of the soil-water balance model, we try to correlate them with yield. So for example, this is the red here is wet, and the other colors are drier. So maybe in this area, in this particular time of the year is wetter, and these are drier. So and then we pick, you know, the period wherein, for example, there is in this case for particular crop like maize and soybean in December to January, this is usually their active period where they do antithesis. And then we tried to build a correlation model, a regression model between, say, for example, the wetness in the soil and during this period and the yield. And you can see the potential of that simple correlation model to predicting the yield about 3 months before harvest. It's not always perfect, but there are red in there. Okay. So I presented several schemes that we have been doing, a simple statistical regression model to mechanistic. And this one is just a step further, where you use a more physically based model and then link it with remote sensing data. This study was done in India. You can see here, it is a part of the irrigation system in the Bahakra irrigation system. This is the system actually, and the study only is done here during 2000-2001 season, and this is for wheat. So the idea is, I don't know anything about the area, and when I went there to collect data, they will not give me data set because I might give it to Pakistan. So, so the only solution I have is to look at remote sensing data. So when the crop models, they need soil data set, spatio-temporal, and weather data. Weather data, we have some measurements in here. So what I hypothesize is what I can see in remote sensing, like for example, fluxes like AT or soil moisture. This represents the characteristic of the system. And then I implemented a simple pseudo-regional version of SWAP, the soil water atmosphere plant model. And what I said is at any instance in time, if I can fit the shape or the distribution of this evapotranspiration from the remote sensing and the model, then I can say that I can probably have an idea of what is in the ground, like soil property or management practices. So what I did is I implemented an inverse modeling algorithm using SWAP and genetic algorithms to characterize the system using remote sensing data. And after that, you can do anything like optimizing management practices given a climate. In this case, if you have seasonal climate, then you can use seasonal climate forecast. So this is the AT for 2 images. I can only manage 2 because I have only limited budget, and one image is $500. That's too much for for us in Asia. And I use CBOL to estimate ET. You can see that, earlier in the growing season, you can see the distribution of ETs, not a lot of ET, but there is a variation. It means there is a variation in what? Soil across the area. Maybe management practices in terms of planting and irrigation. That's why you can see variations here. And as you move along in time, the variation is still there. And then I did a simple classification of where the wheat are and tried to match what the remote sensing data is saying and what the model is saying. Then I was able to get this data on what is in my system, like soil property, irrigation scheduling, quality of water, etc., etc. And you can apply simple management optimization, like when to best irrigate and when to plant by optimizing only yield. And then you can have a result like this, that given this available water and at this climate condition, then you have management practices in terms of here irrigation scheduling, ratio of temperature, actual transpiration and potential, and crop management in terms of planting. So I will not dwell on this. This is actually offshoot of my presentation, but this is the second to the last, but I hope I have time to explain also the 5th one. But I want to spend some time in here improving information for decision support. What are the desired characteristics of an improved information for decision support? I think of 2, lead time and accuracy. Lead time is in order to act early or preempt. So seasonal forecast can play a big role in that as long as there is a scale. Accuracy is related to scale to be able to quantify better. So basically this has been presented by our earlier presenters, but I just want to review, if you want to forecast yield before the harvest at planting, there are 2 sources of uncertainties. One coming from the climate, because you don't know anything about the climate of the season. You know only what happened before. And if you are using a model, either mechanical, statistical, or physiologically based model, there will be always error in your model. But as you move along in time, as you are monitoring more climate information, this error in climate will reduce. But the model will be the same because you're not doing anything in it. So model is not perfect. We can say, okay, there is this small RMSC, but if you apply it in other condition, maybe the model error is always there because the efficiency of the model is always dependent on our understanding of what a biophysical system works, right? So as you monitor more weather data or climate data, that climate component of that error will minimize. But the model error is still there. Seasonal climate forecast may be able to address the blue one like this. And maybe from remote sensing information, you correct the model using remote sensing information, you can probably reduce the red line like this. So I'll present some of the work, how we are doing this one. So linking, he discussed actually about weather generators, but I will explain in a different way, and then show some work that we've been done on data assimilation with remote sensing data, and then plus combining data assimilation plus climate forecast or monitored climate. He presented this, so I don't need to dwell with this one anymore, right? But IRI, we produce seasonal climate forecasts, but in different formats. These are probabilistic forecasts. Probability of above, below, and near normal. Although before that, we have those time series of data, of course, before you can do the probabilistic. Okay, so we know this already. I'll present 2 tools. These are our downscaling scheme also. simple resampler. Just basically, it resamples the historical records based on the seasonal forecast probabilities. So based on if it is above, what is the probability of being above, below, and near? And one is conditional stochastic weather generator. So Dr. Huang touched this a little bit a while ago. So this is an application of a simple resampler with a forecast of, this is actually an actual forecast in Brazil. So 53% below normal, 30% near normal, 70% above normal. And this is very simple because you just look at the historical record and then see, in this season, you categorize them based on above, below, and near, and then just bootstrap it 53 times from your data pool from this particular category. And bootstrapping it will be a block sampling. So you're sampling your data precip, Tmin, Tmax, solar radiation. For DSAT, that is enough. And then bootstrap it many times until such time that the probability is, the number of samples that you need to achieve this probability is completed. So in this case, I want to generate 100 time series of data to represent that seasonal climate forecast of a dry forecast. But I use all the forecast information, not just the bigger probability. And you can see here, this is from climatology. So we run the model using 30 years of data for that season compared to a drier forecast like this. So the model actually responds to the dry forecast. And in here, the planting is in October, and the forecast December, January, February. So October, November is merged. So this is where Dr. Huang was saying that use the observe, forecast, and then as you update in time, use the observe, monitored, longer observe, and then the forecast, et cetera, et cetera. Our stochastic disaggregation based on a weather generator is different. So this figure actually shows the distribution of rainfall based on this forecast. It's still dry, 52 below normal, near normal, and above normal. And this is the climatology of rainfall. And we translated this forecast by using this probability to adjust the seasonal forecast. And this is actually a representation of the seasonal rainfall forecast based on this probability. And our weather generator actually can do for each percentile. So for example, in order for me to produce a distribution of yield, I need to disaggregate different percentile. So in this case, I use 50%. APCC did not like the conditioning of the model parameter in the weather generator, but I presented here if I condition the occurrence model, in this case the Markov chain, an intensity model, in this case the gamma or hyperexponential distribution for the amount, actually I get a better result compared to just matching the amount of the rainfall, in this case amounts. Why? The climatology actually in the area is always wet. So the yield is actually not strongly represented by the seasonal amount, but by the occurrence and the intensity of rainfall within the season. So there is more, if I translate this to intensity and occurrence, I can have a better estimate of the yield in this case. So this is for correcting the model using data assimilation. Like if you have observation in remote sensing, you correct your model. Your model is not always perfect, but there's information in there. Observation from remote sensing is not perfect, but there's information in there. The only the use of the data assimilation is just optimally using this information by combining them. So we implemented a simple filter with the model, in this case DSAT Maize, and then try to simulate Maize in Iowa or any other region. And then this is the result of data assimilation. For Solmosure, this is for LAI. And this is without data assimilation. It's just running the model in aggregate way, trying to match the observed yield from the USD and ASS. Basically, the model is not working well, but then, although it worked actually, because there is a correlation of 0.47, but if there is, if you correct the model, the water balance of the model, and some of the penology, it can work better. But this is only for correcting the model. So now I want to combine correcting the model and then the information from climate using this one with the climate forecast and then with the filter. And then you can see like this. Without forecast, this is my result updating in this along the season. This is the observed. With forecast plus filtering mechanism, then you can have a better estimate of the yield. Unfortunately, the forecast here is climatology, so there's no actually forecast. This is in Iowa, and where the skill is very, very low. Anyway, this is just to show, that you can apply this methodology especially when there is a skill. So I presented this one, how we apply climate information to inform decisions at different scale, local scale, regional scale, and then improving information for decision support. How much time do I have more?
You're still okay with time?
I am still okay with time? 10 minutes, okay. Actually, the next slide is one presentation. Okay, I have 10 minutes.
Oh, you can go.
Okay. Okay. I want I want to present this because I've seen that APCC is using, they use Ensemble, but they, maybe you can learn also from this presentation. Okay. In this presentation, because I've been trying to explore how to link that bridge, that gap between climate forecast and model, as you are doing, right? So I have this statistical downscaling technique using weather generator and resampling techniques, simple resampling techniques. But why not use GZM, daily GZM data or RCM data? So I did this in 2006, I updated in 2008, and then many people have been doing it, and then I said, okay, just do it now. my share is done. So anyway, I tried to see if we can really use daily GCM data for seasonal for crop forecast, because daily GCM can simulate seasonal climate, right? And then I will try to point out why it's not working and how to make it work. So this one. No need. Okay, cropping models require daily weather inputs. The disparity in the scale, the global models are large scale, decision scale are very small. So this figure actually shows the correlation of raw ECAM 4.5 rainfall with the yield of maize, in this case simulated maize, in our study area in Kenya. You can see that it is red. So there is actually a scale of the GCM in October, November, December. This is the short season I was telling to you. But then if you look more into that, you can see that this is the observed yield, i.e. observed yield, because this is the simulated yield using observed weather. And this is actually the simulated yield using the uncorrected ECAM 4.5 rainfall data. You see that the correlation is large, but the bias is very, very big, right? So I said that, okay, where is this bias coming from? I look at the rainfall from the GCM. This is from this station, so I have amount, frequency, and intensity. And GCM actually says that it rains a lot. It rains a lot, but small amounts. There are times that it is okay there. So I said that maybe the bias is coming from the bias in the rainfall. So what I did is I tried to correct the bias in the rainfall by simple bias correction, like mapping the rainfall In this case, I tried to map both frequency and intensity. So I correct the intensity, and then I correct the frequency, meaning the number of days, rainy days, and I corrected the intensity by just using a simple statistical method. Okay? And then once correcting it, then I figured out that the climatology is corrected. I applied the model. This is the uncorrected one. This is the corrected one. But I see that, okay, climatologically, the GCM simulated rainfall is corrected, but why is this bias still there? Then I looked more and then found out that the dry spells are not matching with the observation. So, and I said, what if I can correct this dry spell, and how to correct this dry spell? This is actually what happened, yeah? Sample bias correction of rainfall. This is the one member only of ECAM. I have 24 members. This is the uncorrected, this is the corrected, this is the observed. ECAM is not doing, is doing well actually there, but you can see that rain is clumped compared to here. So if I can mimic this kind of distribution from this one, then maybe I can improve better in my simulation. So I said, okay, I already corrected the frequency. Then the only thing is to distribute those daily rainfall in the time series in a way that it can mimic the observation. So I know this one because this is my pet. And then, so I just link it with this one, meaning I have the corrected frequency. I just have to correct the timing of those rainfall. So we have a simple paper of that if you're interested. And then once we did that, this is what happened. Uncorrected, this is the dry spell length during this period. This period is very sensitive to crop in that case because this is the antithesis period. This is only bias correction, but then when we try to correct the timing, the time structure of rainfall, then we get a better estimate of the dry spell length. And then this is the uncorrected rainfall. This is the bias corrected. This is the observed. When we apply a combined bias corrected with the weather generator, in this case conditional weather generator, then we have a better distribution of rainfall. However, there is still this gap. Why? Because it depends on the skill of the model. The model is not perfect. It only captures probably 75 or 30% of the variance, so the correlation about 0.7. I have more slides, but I don't need to bore you. I want to go here. This is actually the predictability of rainfall using ECAM 4.5 forced by observed SST compared to crude data. And these are historical simulations, so it's not forecast. You can see that the model works well. This is some sort of a reanalysis, if you will. But then, if you look, we at the IRI, when we do seasonal forecast with our two-tier approach, we forecast the SST and run them to the atmospheric model and then come up with rainfall. And that is our seasonal forecast. And this is what it looks like with our two-tier approach. It's yellow, poor. But then for more improved model, this is coupled model, this is NOAA CFS, and you can see the promise. So what I'm trying to see here is, if I have a skill, I am happy. I'll be jumping around because this is what I can translate into information. But in areas where there is low skill, I have still the opportunity to improve that information by merging observation. So